So, welcome to this talk. I think this will probably be a very boring talk to most of you since you're at this workshop. So, whereas Dan promised that he'll give a boring talk and didn't really keep his promise, I hope I can. Anyway, I'll start introducing cryptocurrencies, explaining the basics of Bitcoin. What are transactions? What is the blockchain, even if you've already seen it? Quickly, what is consensus? Or in other words, how can everything that we've learned about consensus so far be used to create the cryptocurrency? And in the second hour, I'll talk about a little bit more advanced things, in particular how the concepts that we've learned about during the first days of this boot camp can be applied, in particular zero-knowledge proofs, snarks and so on, to improve on what Bitcoin gives us in terms of anonymity, scalability, and expressiveness. But first, let's start with some history. Where did it all come from? Classical eCash. How did cryptographers think about these concepts back in the 80s? So before Bitcoin eCash, the goal of eCash was really to have a digital equivalent of physical cash. So the economic model was basically the same as with regular currencies. So the concept was introduced by David Chaum in this paper in the 80s, where he also proposes the concept of blind signatures without actually instantiating it. Very visionary. So the model is that you have a bank that emits coins, and Alice can go to the bank and withdraw a coin, and her account gets debited. She can then spend the coin with merchant Bob. And if Bob brings back this coin to the bank, he gets his account credited. So what we want is some digital object that's hard to produce, like physical coins. So using cryptography, we have such a concept, which are digital signatures. The problem with digital signatures, or with any digital object, is that contrary to physical objects, even if they're hard to create, they might be easy to copy. So the main problem with all these eCash schemes was to solve the main task was to solve this issue of double spending. How can we prevent Alice to take her coin, spend it with Bob, and then take the same coin again and spend it with Charlie, which would not really yield a reasonable currency system. And the main preoccupation, at least in the 1980s and with everything that came before Bitcoin, was anonymity. How can we protect Alice's anonymity in the system? How can we guarantee that the bank does not know that this coin that comes from some, say, shady shop was spent by Alice? So digital signatures, I guess all of you know, there's a key generation algorithm that gives you a secret key and a public key. With a secret key, you can sign documents. This creates a signature, which is then verified using the public key. So David Chaum's idea was, and they should be unforgeable. So David Chaum's idea was what he called blind signatures. So can we have a protocol where we have a signer that holds a public key and the user that wants to obtain a signature on the message M without the signer learning the message? Okay, so. And it turns out that if we have something like that, then we actually have a basic system of electronic cash, which works as follows. So when Alice wants to withdraw a coin from the bank, what she does is she chooses a random serial number. She then runs this blind signing protocol with the bank. So she obtains a signature from the bank on the serial number, and that represents her coin. Spending this coin is very easy. She just sends this coin consisting of serial number and signature to the merchant, and the merchant can deposit it back with the bank. So how does this very simple scheme prevent double spending? Well, the merchant will only accept this payment after asking the bank whether that particular serial number had already been spent, and only then give out the goods. So double spending is solved by having online verification. And anonymity follows due to the properties of blind signatures. So this was a very quick introduction of what electronic currencies, or electronic cash at least, looked like before Bitcoin. So there were, like David Chom had his company called DigiCash, but somehow it never led to widespread adoption. Now then, a few decades later, Bitcoin arrives and becomes the, I guess, arguably most successful ever digital currency, but changes the approach quite drastically. So there's no more centralized authority that issues coins. Everything is decentralized. There's no bank. There is hard-coded inflation, which I guess is something orthogonal to how the system works, but which arguably led to early motivation of people to invest in Bitcoin and ultimately to its success. And contrary to all the cryptographic eCash before, there's no strong guarantees for anonymity. So the notion that we get is pseudonymity. How does it achieve that? It maintains a public history of all transactions. So instead of having a bank that checks which coins have been spent, now this is public and distributed and guarantees consistency. And by using consensus mechanisms, there's no trusted authorities at all. Okay, so I guess it's hard to explain how Bitcoin works because there are several components that are combined in a very clever way, and one component depends on the other, so I guess we have to start somewhere. And that somewhere where I start is the public ledger. And let's for now assume that there is an authority that everyone trusts that maintains this public ledger and that will publish updates of these ledgers. So the ledger just contains all the users and their account balances. And now if Alice wants to spend the coin that she owns and give it to Bob, she will just contact the authority and say, please send this coin to Bob. The authority will produce an updated version of that ledger. So that's basically, I guess, if you have a trusted authority, it's the simplest banking system that you could think of. So the way Bitcoin works, it's a bit differently, namely that there's no notion of accounts and account balances, but what it instead does, so the entries in these ledgers are transactions, which basically has the same outcome. Namely now, if Alice wants to transfer 1 Bitcoin to Bob, it's not that we can look up whether she owns it, but we can look up whether she has received it at some point. So if Charlie gave Alice a Bitcoin at some point, then she will be allowed to transfer it to Bob. And this is how transactions in Bitcoin work. So if you want to spend something, you reference the transaction where you've received that something. But what happens if Alice does not want to? So if Alice has a Bitcoin and she only wants to spend half of it to Bob, then the way Bitcoin works, you always have to basically consume the whole transaction, because that makes handling double spending easier, because then you can just say whether a transaction has been consumed or not. So the way we get around the problem of spending all of it is that we allow a transaction to have several outputs. So what Alice would do is she would spend half a Bitcoin to Bob and half a Bitcoin back to herself. And now she can later reference this transaction output and spend this money to say there. So there's no notion of accounts in the blockchain. The only type of information in this ledger for now that is stored there are transactions. So actually, for now, we've assumed more than an authority that publishes the ledger from time to time. We also basically assume that people can talk to this authority, that this authority will say, yes, you are Alice, you're entitled to spend your money. So let's first solve the problem of how users identify. And this is done using the cryptographic concept of digital signatures. So if we want to simplify how Bitcoin works, then we could just think of a public key corresponding to a coin. of a digital signature scheme. And whoever owns the private key that goes with it owns this coin. So that's the definition of owning a coin, knowing the private key associated to it. So Alice owns this public key PKI if it's in the ledger. If she wants to spend money to Bob, then Bob, let's say, creates his own public key, PKB, and Alice will then sign a transaction that says transfer the value from PKA to PKB. So now we've already got rid of identities. All there is left are public keys, and this is the notion of anonymity or pseudonymity that Bitcoin gives us. So again, we have this issue of double spending. How can we prevent Alice to spend her coin with Bob and with Charlie? Well, we're still assuming that we have this authority that takes care of everything. So the authority will accept payments, new transfers, only if Alice has that money, in that she received it at some point, and in that there's not yet any transaction that has spent the money. Any questions so far? I guess I'm not telling any new concepts to you. Anyway, so now interesting part. How do we eliminate this authority? How do we decentralize this concept? So we have this authority that checks validity of the transactions and that publishes updates of this ledger from time to time. And the concept that does this for us is the blockchain. What is a blockchain? It's basically a different way of structuring this ledger. So instead of having a ledger to which I always append transactions, I just append blocks of transactions to this chain. What do these arrows mean? So what does it mean for this chain to be chained together? That's done using a cryptographic hash function. Cryptographic hash function is a function that is compressing, so whatever size of document you put into it, the output will always be 256 bit long. And it should have some security properties. So typically we want small modifications of the input to lead to big modifications of the output, or in other applications we assume that the output really looks random. It should be hard to go backwards to find a pre-image. But the property that Bitcoin basically needs, okay, so here's an example of if I use char1 because the output is shorter. If you hash this sentence, you get this hash value. If you change one entry, you get something looking completely unrelated. So the property that Bitcoin needs from a hash function is that if I want to find an input to the hash function so that the output lies in a certain subset of all possible hash values, then the best way to find such a document is to basically keep trying hash values. There's no shortcut to finding such an input. Okay, so this means that, this effect of small changes leading to big changes in the output, or leading to changes, at least for computational adversaries, has the following effect, that if I have such a blockchain, so what's the blockchain? It's blocks where each successor block contains the hash of the preceding block. So if I change something here, then the hash value will be different here. So this block will be different, and that propagates through, which means that if I change something somewhere, I will change the last hash value. So this can act as basically the fingerprint for the whole chain. Okay, so how is this blockchain used in Bitcoin? So what happens if Alice wants to send her money to Bob? She will create a transaction. She will then broadcast this transaction to everyone. And someone, we'll see who, will take new transactions, put them into a block, and create a new block and append it to the blockchain. But who does this? So the goal was to have a completely decentralized system. So there's no authority that we can that could take care of this. There's only users, and everyone is equal. So one idea we could do is just pick a random user and let the user add the next block. And if enough users are honest, then this should lead to consensus. Except that if it's completely decentralized and we don't have any means of authentication, and there's also no means of, there's no concept of what a user is. So if I have an adversary, he can just pretend to be a billion users. And then if there's just a lottery that picks a random user, the adversary would almost always win and could subvert the system. So that's called a Sybil attack. So to prevent this, the concept of proof of work was introduced. And that's basically a concept that predates blockchain. So it's one of these ingredients that existed that Nakamoto basically combined in a very clever way to construct Bitcoin. So what was proof of work first envisioned for? It was to prevent spam email. And there is this system called Hashcash that lets you do it. So basically the idea is, what's the business goal or the business model of spammers is they just send out millions of emails because it doesn't cost anything, and if someone falls for the trick, then that's good enough. But if the spammer had to work, let's say, a few seconds for every email that he sends, then this would not be a viable model anymore. So how does this work? And apparently there's even spam filters that give you credit if you add such a header. So if you want to send me an email, then you will add a header that says X hashcash. That will have my email address, it will have the current date, and it will have a random value. And now I will only accept that email if this header hashes to something small. In particular, let's say a value that starts with 20 zeros. Okay? So if you want to send me an email and this most likely doesn't happen to be very small, what can you do? Well, there's this random value here that you could just change and hash again. And if you're still not below the target, you try again, you try again. What's the probability, or what's the expected number of tries you have to do before you get one?
2 raised to 1.
Exactly. So if it's 20 zeros, then it's 2 to the 20. So that will take you, let's say, a second, whereas me verifying that you've solved this proof of work is very fast, because I only have to hash once. So there's this nice asymmetry between someone proving work and someone that actually has to do work and someone just checking whether the proof is correct. So that leads to the concept in Bitcoin called mining, where if you're a miner, so you want to create a block, you want to contribute to the system, you collect transactions, but then the protocol says, well, this block is only a valid block and others will only accept it if its hash value is below a certain threshold. And how do you guarantee that it is? Well, you solve this proof of work. You have this random nonce that's contained in your block, and you keep sampling fresh values until the hash value of the block happens to be small enough. So now the idea is that proof of work prevents Sybil attacks because everyone's chances of finding a valid block are proportional to their computational resources and not to how many identities they pretend to be. So if I'm a miner, I want to create a new block, I collect transactions, I solve the proof of work. If I'm lucky and I solve it, I just broadcast this block to the network. So what do other miners do? That's what the protocol specifies, and we'll see that that's also a good strategy to follow. So if I'm a miner, I receive a new block, I check that there's transactions in it. So I have my local blockchain, I check that the transactions in this new block are valid, so they spent money that actually existed in the system. it contains the hash of the last block that I have, so it really extends this blockchain. And I check that the hash value is small enough, so the miner really has solved this proof of work. And if all these conditions hold, then I say this is a valid block. I'll append it to my local view of the blockchain. And if I want to extend now the blockchain, I will work on extending it after that block. So now, of course, the question is finding a value r such that this hash value starts with 150 zeros is a lot harder than this hash cache I showed you. So why would anyone do this? Because you pay them. But who would pay them if we want to create a decentralized system where there's no authority? Well, the nice thing is that what we're creating is a currency, so we can use the currency to pay the miners. The currency will pay for its own stability in some sense. So the incentive for getting people to try to mine new blocks will be the reward that they get in terms of newly created bitcoins. So what the miner will do is, in this block, he will also put his public key, and then by definition of the protocol, this public key gets assigned a certain amount of freshly created bitcoins. How many? Well, it depends on what year we're in. So this, now I come to this inflation, this controlled inflation or limited inflation that I mentioned at the beginning. So the protocol specifies that for the first 4 years of its existence, when you mined a new Bitcoin block, then you received 50 new Bitcoins. For the second 4 years, you only get 25, and so on. And this reward halves every 4 years, and now the current reward is 12.5 Bitcoins. So this will approach a maximum number of Bitcoins that will ever be created, according to the protocol, which is 21 million. So that was...
when is the next event?
When is the next event?
Next year.
It's basically every 3 years.
Yeah, so why every 3 years? We'll...
Well, it's every like something
Over fall.
2040 something.
Date. What's the date?
well, it depends, right? If not, because it's not really in 4 years, it's in terms of number of blocks. So it depends on how fast they're really mined, which brings me to the next point, so I'll quickly mention that. The question was, so what we wanted, or what the Bitcoin protocol wants, is that there is a block every 10 minutes that is created. But now people just work in an uncoordinated way and try to find blocks. So how can the protocol guarantee that this happens every 10 minutes? Well, there's one parameter that it can tweak, and it is how difficult it is to mine blocks. So what Bitcoin does is that every 2 weeks, or every 2016 blocks, the protocol will check how long it actually took to create these many blocks, and will then adjust the difficulty. So the expected, assuming that the computing power stays the same, the expected time it takes to create the next 2016 blocks will again be 2 weeks. So the reason why everything actually takes less than 2 weeks is because up until now, most of the time, the computing power was increasing. So these 2016 blocks always took shorter than the 2 weeks. That's also why the inflation schedule is kind of ahead of time. Any other questions?
So, when we say the protocol, what is the protocol?
The protocol is basically, well, the specification is if you download the Bitcoin reference client, that specifies what protocol you should use. And then you could argue, although with selfish mining and other attacks, it's not so clear to what extent this is true, but at least that's what we observe. It is a rational strategy to actually follow exactly this protocol. So now you might ask, but there's no clock in this protocol, so how can the 2 weeks be determined? Well, you just take the actual time you allow for some slack of people having non-synchronous clocks, and then people just, if someone to calculate the new difficulty use something that's way off your own clock, you will just reject that block. So again, it's in the interest of the miners to stick to their view of the actual time.
Is this 150 the right number for now? That's.
I don't know. So I think I didn't adapt it. So I given this talk a while ago, and I know that in between it definitely was less. But what I looked at was the energy consumption, and that's basically back to that, which means that it's probably assuming that electricity didn't change that much, or mining hardware, it's probably around this. Yeah.
What's the number 150? Number zeros?
Zeros, yeah, in a binary representation of your. I mean, if you look at the amount of hashes the Bitcoin miners produce, it's just.
Not 2 to the 150.
Per 10 minutes.
2 to the 150 is a large number.
I know, but it is basically. So I've seen talks by people talking about what's the computationally most complex objects that mankind has created, and people argue that it is the Bitcoin blockchain. It is the object that most computational power went into to create it.
Most computational power consume, or what do you mean by most computational power?
With all the energy.
Like how much? I mean, well, I guess it's both, right? Computing power in terms of how many operations, but also in terms of how much energy consumption. If you talk about like computational objects in whatever definition you take. Okay, let's continue. Hugo will tell us if it's true. Are you checking?
Difficulty is 10.18 T. Yes, there are. I don't know
hashes.
how much is there?
81 exahashes per second.
Okay, so it's way beyond tera.
How much is it?
81
Exa, and exa is how many tera?
10 to the power of 18.
Yeah.
So 81 times 10 to the power of 18 hashes per second.
So it's more like 50, not 100.
Oh, but they add the 30, there's another 32 that they added.
Okay.
It's a lot.
Yeah.
It's not important. I just was curious.
Okay. Yeah, maybe I got it wrong. But it sounds a lot. So what happens if there's a fork? So everyone mines, everyone has their local view of the blockchain. So even if everyone had the same view, what happens if two miners find a block at the same time? But the transactions that they include differ. Would it be a problem? I claim it would be, because it would enable double spending if we accepted both blocks, because this would be a valid block because consistency is checked with respect to its own history, and so would this block be. So that's something that we do not want. So the way that the protocols specify of what you do if there's a fork is called the longest chain rule, which says that if you look at all the blocks you can find, you can construct your local blockchain, all the blocks that reach you, and you take the longest branch of this chain and you consider this to be the state of the system. And if you're a miner, then you will try to extend here. What happens if you see 2 blocks? Then the protocol just says accept whatever you saw first. That's a specification.
There's no reason to, if by chance they are completely disjoint, to add them both.
No. The problem would be that you want the chain where every block has the hash of the previous.
Right. So in this case, you can hash the 2 previous and come back. Do a diamond.
Yes, there's actually proposals that try to get bigger throughput by not having a chain but having a DAG. So yeah, but of course the problem is then it gets a lot trickier to make sure there's no contradicting transactions. Okay, so what happens if this is my view? I'm a miner, I try to mine here. If then a block arrives, this one I saw it first, so I keep mining here. By the way, I could really, I mean, it's not because I've already spent a lot of time mining here that I should continue, because it's basically a memoryless process. I mean, it's not that I increase my chances of finding a block because I've already tried for some time. But I guess the heuristic is that if I've seen it first, then a lot of people have seen it first, and then it's rash. You always try to do what the majority does. But if then another block extends this branch of the chain, then I would switch and I would try to extend here. So if this is, let's say this is the network of Bitcoin miners, so the nodes would be miners, the edges would be their connections. Then suppose we have a state where everyone, this is basically the blockchain they see, the star block is the last one. So what happens if two miners at the same time find a new block? So here the triangle is found, and here the nabla is found, and everyone propagates this new block to their neighbors, which means that at some point the network could be split. Half of the people believe that this is have seen this block first, so they consider this as the last block, even if they later see the other one, and here's the other way around. Okay, so there could be temporary inconsistencies. However, and this is related to what Raphael talked about yesterday, that the time it takes on average to create the block must be a lot longer than the time it takes to propagate the block. Because in this case, it means that it's already these events are unlikely, but these events, the fact that these events keep occurring is even less likely and decreases exponentially. So what would typically happen is that at some point somewhere someone will find a new block. Let's say it was in the triangle camp, will propagate it. These miners will see this new block and will then stop considering the nabla block as the last one, and everyone will reach consensus again. So this works if the majority of the computing power follows the protocol, whereas it completely breaks down if this is not the case anymore. So for example, if Alice has the majority of the computing power, then what she could do is what's called the 51% attack. She could buy a car and pay Bob. Bob will then, because the protocol specifies so, not immediately hand over the car, but say wait 6 blocks, which is the time that Bitcoin recommends that you wait until you consider a transaction to be settled. And after 6 blocks, we'll hand Alice the keys to her new car. Now, if Alice has a lot of computing power, more than half of it, then what she could do is she could revert this payment by basically spending her transaction that she's spending to someone else, and then keep mining here. And if she's got more than half of the computing power, then at some point with almost certain probability, she will overtake the honest miners. And now even the honest miners, since they follow the protocol, will switch to Alice's chain, which means that this will be the chain that is considered to be the actual state of the Bitcoin network, and Bob will not have his money anymore. Yeah?
So miners are listening for transactions, right? So
yeah.
Is it possible that the same transaction appears in, let's say, 2 consecutive blocks that are mined by different miners?
Yes, but no one would... Okay, so you mean if this transaction happens here?
No, I just mean PKA to PKB took a while to propagate through the network, and the first miner who won saw it first, one added the block to the chain,
Yeah.
and then by the time it got to the second miner,
But the question was, what does the second miner do? Does he try to extend this chain which already contains the block of the first miner? If so, he would not take the transaction because he would view it as illegal. And if not, then it's a fork anyway. And all we care about is that every branch locally is consistent with respect to transactions, and forks are resolved by the consensus mechanism. So, sorry, yes?
Would you be able to go over the statistics as to how the 6 blocks got derived? As like,
I think that's. I mean, if you read the original paper, it's very like hand wavy probability analysis of just like what's the let's say the adversary has 49%. What's the probability of still the adversary managing to overtake six blocks of the honest users? And that's, I guess, was considered a low enough number to recommend that. And I mean, I guess it's also probably also contributes, since it's 10-minute block time. It's 1 hour, and it makes it an easy constant, I guess.
So maybe, I mean, the analysis is in one of the lectures from yesterday, right? So,
but where he justifies exactly the 6 blocks.
Well, the 6 blocks are just justification of as a function of the probability that something happens. I think it's case stability and.
Yeah, but I guess it's some. Yeah, it's derived from some probability being low enough to be acceptable as failure probability.
Yes. So, were you here yesterday, or?
yeah, but I don't think that I went to that one.
I mean, that was Rafael, I think.
Yeah.
I mean, his only answer was that 2 to the minus 6, how it compares to Visa fraud. But
okay.
it's not a good comparison.
Like it's 2 to the minus 6 if we think the adversary is 50%.
Yes, yes. In that case, if you bought a car, I don't think it's 2 to the minus 6 is confident.
Yeah. It's. I mean, but that's also the nice thing, is that you can yourself decide how much risk you want to take, how long you're waiting, and if you. There's like these fast payment protocols, they don't wait that long. If you want to buy a coffee with Bitcoin, that's the easy. Make an easy payment.
I have a question.
Yeah.
Maybe it's just a matter of terminology, but why do we call it an attack? Blockchain is built to be controlled by the majority of the computing power. So
well, in this case, it's an attack because it deviates from the protocol, right? If this happens by, I mean, the fact that Alice creates 2 transactions that spend the main coin is already an attack. It's not something that can happen by chance. It's not. I mean, you could say that, yeah, if some pool has more than 50%, they can.
it's logical. If you have 51% of computing power, you control the network.
Yeah, but it is. But you control the network, but you still. I mean, what makes it an attack is deviating from the protocol by creating 2 transactions that represent the double spending. So the attack is not that someone can overtake the chain because they have a lot of computing power, but they do it because they want to undo a payment that they had made before.
But it is public because everyone can see that there is a transaction which is not, which violates the.
Yeah.
It was in a conference where was a lawyer that got asked if double spending is illegal. His answer is like, obviously, he stole money. Like, the judge won't care like about all those details. You did double spending. Like, you told somebody you were giving him money, you didn't give him money. It's illegal. I know you can argue with this, but I just wanted to quote this. Like,
yeah, I mean, yeah, I agree. It's because you're trying to undo the transaction that makes it.
Maybe should be 51% crime.
Okay, so now that we've seen all the components of it, how does it work? How does this self-enforcing mechanism work? So the miners are incentivized by reward. So if Bitcoin has some value, then it's rational to try to mine and follow the protocol. The probability of mining a block is proportional to the computing power. So the problem of Sybil attack is avoided. And it is rational to mine on the longest chain. And since, like, if the majority of people do that, then you get a quick consensus. So basically what we've seen so far was if we had a trusted ledger, then we could use it to make a payment system. If we have a payment system, we can use it to pay miners. And using these miners, using the proof-of-work consensus, the Nakamoto consensus protocol, we can actually avoid this trusted party, this authority we assumed in the beginning, and replace it by this consensus protocol. So it's this self-reinforcing cycle of different ideas that basically makes Bitcoin what it is. That's how I see it.
So if the money is created by the miner from the beginning, how did Nakamoto pay itself?
Well, Nakamoto did all of the mining Nakamoto did all the mining in the beginning.
Difficulty was low. It was easy.
Yeah, exactly. So if if the difficulty changes a lot, then this.
In economics, it's called a pyramid scheme.
Well,
in economics, it's called a pyramid scheme.
So we know the public key of Nakamoto.
And some of us were very smart to understand that it's a pyramid system, and we didn't mind when it was cheap.
I heard at the beginning, you have a PC, you can mine a lot of coins. Right now, it's impossible.
Yeah, and so you can actually, since all the transactions are public, then you know which were the blocks that Nakamoto mined. So you would see whether Nakamoto reappears and tries to spend his bitcoins. And people are watching that, but it hasn't happened so far.
He lost the keys.
Yeah.
That's why he's not coming.
And nobody will trust him if he draws computers.
There is somebody who is instructed to pay 5 billion or something, and he says he's Nakamoto. It's in the news now.
Now, or was it the... No. Okay, no. Well, I think if you're Nakamoto, it's very easy to prove if you haven't lost all your keys. Okay, yes?
So after everything we've seen maybe like yesterday and today, like in what sense can we say that it is rational to mine on the longest chain? I mean, clearly like that's there are many reasons to do it, but then there's also these considerations like established mining. So when we make such a statement, is it because
No, it's all. This is like the hand wavy and overview talk. But I guess you could argue with Vasilis and say that, well, if selfish mining,
then Bitcoin wouldn't exist, right?
Yeah, so we're viewing it basically as an empirical statement that we can analyze under certain assumptions. For example, when we have specific utilities and fixed difficulty, that's one setting where we can understand why this might be rational. And we can maybe pose as an open problem to find some, to relax some of these assumptions and provide a rational analysis to mine on the longest chain nonetheless.
By the way, was it rational to pay for Bitcoin at the beginning? To buy Bitcoins to mine?
Is it rational to buy Bitcoin now?
It's a good question, right?
No, now at least we know that it has value. At the beginning...
How do you know it has value?
No, of course you are.
People are paying for it, but doesn't mean that is value.
No, it has monetary
This is a
value.
very interesting question, right? So either it was rational, and most people in this room are irrational, including because we didn't do it, or it's not rational, and some people are irrational. It's unclear. I mean, you can.
But do the models can say anything about how rationality moves? I mean, no.
So there were to try to explain pyramid schemes. I mean, I was not joking. Pyramid scheme is when people who enter first gain most, and slowly people gain less. And there are models in ecology that try to explain how these things people
Like this.
You ask a question outside the system. If he knew how to answer this, I'll go with him with the real stock market, not with Bitcoin.
even a posterior.
Like rational is not a great word here. No? Like you can ask, was it rational to invest in Amazon? And the question, the answer should be like not whether it was rational or not, as it should be something about that was a risky investment.
Yeah.
It should depend on your risk tolerance, so some possible reward and some possible like loss.
I guess it depends on the beliefs you had at that time, whether it was rational or not.
It's a belief. You don't have analysis to do probability or anything.
Yeah, so when you talk about Bitcoin is different from Amazon in the sense that the best case for Bitcoin is something that's in econ referred to as a rational bubble, where if you own stock in Amazon, you want to own it regardless of whether anybody would buy it from you, because Amazon will pay you dividends. Even if you're holding a stock of Amazon and you're not allowed to ever sell it, it's still valuable. A Bitcoin that you're never allowed to sell has no value whatsoever. So in that sense, it's different, but the dollar bill is much more like Bitcoin than a stock in Amazon. If you're not allowed to transfer a dollar bill to anybody, it has no value. So when you were an early investor in Bitcoin, you were kind of betting on it becoming something that people use for trading a currency. And this, and if you're mining now doing this, you're essentially doing this bet as long as you're planning to hold Bitcoin for a year. It's uncertain what the value of Bitcoin will be in a year. It could be zero.
Okay, so that was a very, let's say, bird's eye overview, where I sweep a lot of details under the rug. So let me mention some of them. So actually in Bitcoin, it's not true that a public key corresponds to a coin, but there is actually somehow a notion of accounts, which are the Bitcoin addresses. It's not that there's like in the blockchain, it says nowhere which address has how much money, but you can deduce it by summing up the transactions. So what's an address? It's actually the hash of a public key, public verification key for signatures. And when you sign, then of course, in order for a signature to be verifiable, you also have to provide the public key. Now, how do these transactions look like? So the simple case would be if Alice has 6 Bitcoins, she wants to spend 6 Bitcoins to Bob. Then she produces a transaction that has Bob's public key here. It's actually his address, but let's forget about this for now. And provides a signature that authenticates that these were her 6 Bitcoins. If Alice doesn't have a 6 Bitcoin bill, but only two Bitcoin coins and 1 3 Bitcoin coin, what does she do? Well, she does it like with physical cash. She will give all of this to Bob. This is possible because transactions can have multiple inputs. And luckily, they can also have multiple outputs because otherwise she would have overpaid Bob. So what she can do is she can send the remaining Bitcoin back to her own address, and this would be the change that she takes from this transfer. What she actually does is that this would not be 1 Bitcoin, but let's say only 0.9 Bitcoin, because it's all about incentives. So if you want your transaction to appear in some block, then you better pay the miner to include it in his block, because otherwise, why would he do that? It only makes the block bigger and therefore slower to traverse the network, and therefore less likely to end up in the longest chain. So what Alice does is, or what transactions allow you to do, is that the outputs can be smaller than the inputs. As long as they're not bigger, this transaction would be valid. And the miner that takes these transactions per protocol specification earns this 0.1 Bitcoin as a transaction fee. So if it ends up in this block, the miner that created that block gets the transaction fee. So just to recap what I said before. So say Alice paid Bob, so Bob now owns this 6 Bitcoins. What does it mean for him to own it? To know the secret key that goes with this key, with the public key that's mentioned in this transaction. So what Bob can do is he can create a new transaction, spend these 6 bitcoins by basically referring to it. So this input says, now I'm spending the output of this transaction that's already in the blockchain. Bob has to authenticate it, otherwise anyone could do that, by giving a signature that's valid under his public key. Okay, so that's like the standard type of transaction. And the other one would be the miner that wants to spend the money that he's created by creating this new block. So what he could do is, remember, the miner put his public key inside a new block. So he could also create a new input, a transaction with an input that refers to this block. And by definition, the value of this input is whatever the newly created bitcoins were, plus all the differences of output and input, which would be all the fees that appear in that block. So if this is the only transaction, then this would be 12.5 plus 0.1 bitcoins. Okay, is it all good? Well, I guess one of the drawbacks of Bitcoin is that it's very slow. So the reason is that there is a block size limit. So you can only fit so many transactions into one block. The difficulty is adjusted, so there's only one block every 10 minutes. So this leads to about 7 transactions per second, which for a global payment system is very little. And it can also become very expensive. So if you look back in January 2018, when the Bitcoin had its all-time high and people were transacting a lot, the transaction fees went up to more than $30. So then it became really costly to transfer Bitcoins.
It's mining fee or transaction fee?
Pardon?
You're talking about transaction fee, right?
Yeah. Yeah, the transaction fees.
Should be transaction fee on the side, not mining fee.
Oops, yes, transaction fee. Yeah. Yeah. Fees that go to the miner. Yeah. There's, I'll talk about this in the second hour. There's some solutions that basically allow you to use Bitcoin to secure payments without the payments actually all happening inside of Bitcoin. So this could be compared to, I don't know, back in the days when there was still the gold standard, the banks or the national banks, they had their gold reserve, but they wouldn't pay other states by moving the gold reserve, but it was there as the store of value. So there's tricks how you can do transactions that are as secure as Bitcoin transactions, but you don't need to put everything in the blockchain. Second problem is drawbacks of proof of work itself. So what happened, the way Nakamoto envisioned it was that it will be very decentralized because everyone that has a computer can just use her spare CPU cycles to mine. And then if everyone in the world mines, then that's very nicely distributed and hard to get a 51% majority. What actually happened is that specialized hardware was created. So now if you mine with your computer, then you would actually pay more in electricity than you would expect to gain in Bitcoin. So you have very big investments to buy this specialized hardware to mine efficiently. And then you should also have cheap electricity to compete against other miners in other parts of the world where it's cheaper. So this led to a mining oligarchy, which I guess contradicts somehow this approach or this ideal that it should be very decentralized. What I think is the most problematic, yes?
The miners get is imprinted in the software, or now people can offer or something, or how's the fee?
The fee or the reward? The reward is what the new Bitcoins that are created. That's basically specified by the protocol. The fees, it's...
One transaction before, you have 0.5 transaction went to the miner.
Yes.
Where is this 0.5 transaction determined?
If you want your transaction to be... it's you who decides. You create the transaction, you specify what is the input, what is the output. The difference is the mining fee, it's up to you. If you put 0, no one will take it. if you really want the transaction to be included quickly, then you put more fees. Then it's in the interest of the miner to immediately include it because he has the money. So it's a market, and that's why in January 2018 it went up so much, because there were so many transactions that were not being processed because there was so much demand on Bitcoin transactions. Yeah, so I think the biggest worry of Bitcoin and using proof of work is the electricity consumption, which is, if you think about it, there's this website that tell you what's the country that's most close to how much Bitcoin consumes, and right now it's Austria. So Bitcoin mining consumes as much electricity as all of Austria, which leads to a lot of pollution. I guess Bitcoin fans will tell you, yes, the banking system also spends a lot of money or needs a lot of electricity. But I think if you compare the fraction of what Bitcoin represents in global payments, it is very much more expensive than any other means of payment.
I noticed that Chase banks leave the light open at night.
Yeah, but I think it's still compared to what Bitcoin consumes. Marginal.
The first one, right? That's actually the real thing.
I mean, this if you care about your investment, this if you care about your future, I guess.
None of us can mine, right?
Yes.
You have to generate these hardware, you have to be close to cheap electricity.
Yeah.
It's a monopoly of very few places in the world.
Yes.
It's not clear, it bothers a lot of people, but there's not a lot of good kind of rigorous arguments why it should actually bother you.
I think so there's one argument that's actually why it's good, because all these mining farms, they've invested so much money in their mining hardware, which they can only use for mining, so that they really care about not ruining Bitcoin and avoiding any kind of collusions that would undermine trust in the system, because they have so much stake in it. So it could also have a positive effect.
Same they're like banks.
Yeah. They want people to trust them. Yeah. So let me conclude by saying there's other means of. Yes.
Another question. How about the mining pool? Because pooling is probably one of the main directions.
Yes.
And it goes against democratization, let's say, because and that is one of the main problems.
Yes, mining pools as well. I guess it's related, but again, there were times where I think if two of the big mining pools had colluded, they could have launched 51% attacks. But again, I guess it would be, and that's something which in the game theoretic analysis we saw is not factored into, which is that it's in their interest not to harm trust in the system, because otherwise they would lose their investment.
They make a lot of money every year.
Yeah.
There's
There's no reason for colluding.
Continue being a monopoly. Monopolies have that advantage.
Yeah. But it's not in the interest to use this to subvert the system.
No,
yeah, exactly. They want to continue printing money.
But, if I want to mine, of course, I see if I don't have enough computing power, it's useless. But if I participate in a pool, I can get a reward. That is the difference.
You probably cannot. You have to spend, even participating in a pool, you have to spend quite a bit of money and live in a very special place with very cheap electricity in order to participate.
Well,
go online and try to participate in the pool.
This is for Bitcoin, right? You can do these things in other currencies with lower difficulties. There's 2,500 cryptocurrencies out there, so.
Yeah, sure. Then it's a different problem, right? Then the 51% attack does become more.
Well, we've seen 51%.
The public keys are registered on the ledger. So if I'm a Bitcoin owner, I will not lose my public key because
the secret key,
it's out there in the cloud, and I'll always be able to access it.
No, but you need the secret key in order to spend the money that you need the secret key.
I need the signature. The signature. I can lose the signature.
Yes, yeah. Exactly. That's basically what makes you own the money, because you know the secret key. And you can create signatures.
What is the solution to not lose the signature? It's a big numbers. What is the
You write it down on paper.
You write it down on paper?
Yeah.
How long it is?
Seriously, people do it, and it's one of the best ways.
I'll keep it for you.
Escrow.
And yeah, I'll call myself an exchange, and I'll get a lot of people to do it.
And then you disappear.
Or
you get hacked.
Or I just take fees, and anyway, there's a lot of it. But just start by, I'll take care of you.
This is the problem of public. Remember something big.
Okay, so there's many ways. So I guess the most promising alternative to proof of work is proof of stake, which we'll hear about tomorrow. So proof of work means that the probability to mine the next block is proportional to your computing power, and proof of stake it would be proportional in how much stake you have in the system. That is typically how many coins you owned, or some product of number of coins and how long you have owned them. The big advantage is you get rid of this energy waste, but there's of course disadvantages as well. There's plenty of so-called nothing at stake problems that you have to overcome by clever protocol design, and you will also have there's no more in Bitcoin. You have users and miners, and they're separate. But in proof of stake, it's basically the users that become the miners. So that could also lead to problems of participation. Although I guess delegation can get rid of that. And there's also other proposals where you want to avoid, or let's say, where you still want to have some extrinsic commodity that you use, like computing power. But it should be something more sustainable. For example, there were proposals to use proof of space, where if you want to mine, then you have to allocate a certain amount of hard disk space to the mining process, and then you prove that you've actually done that, and then you reward it according to how much space you've allocated. And that concludes the first hour. Thank you.
Resume at 3:30.